Hello, everyone. I'm Xinrui Zheng, comes from the Institute of Parallel and Distributed Systems at SATU. I'm here to discuss a bottleneck that sits at the intersection of AI and storage. As large language models move from massive data centers to our personal laptops, this work, SolidAttention, we're proposing a way to the long context models on consumer-grade hardware that has constrained memory capacity. To solve the problem, we must first look at the two phases in the LLM inference. In the prefill phases, the model digests the entire problem at once. It's computationally heavy, but highly parallel. But once we start generating text, we enter the decode phase. This is sequential and auto-regressive. Its new token depends on everything that can be fed. To avoid recalculating the entire history for every single word, we use the cavi cache. But the cavi cache has a massive footprint. The cavi cache grows linearly with the context length. If you are running a standard Llama 3 8B model with a 128K context, you need over 16 GB of VRAM just to store the cache. This is about 4 times of the model size. It is necessary for tasks like document summary or coding agents. However, most consumer laptop GPUs only have 8 GB VRAM. Even higher-end laptops rarely exist 16 GB. As soon as you try to have a long, meaningful conversation with a local AI, the systems run out of the memory and crashes. Not to mention that when using a laptop on a daily basis, you need to reserve some memory spaces for the OS and other applications. The industry's current band-aid is interval quantization, compressing the cache. It helps, but it's a destructive process. In long context scenario, certain tokens act as anchors with high magnitude outlier values. When you quantize this to 4-bit, you lose the precisions. Our benchmarks show that while 4-bit quantization saves space, it causes significant accuracy drops, especially with long context. We wanted a solution that saves memory without compromising the model accuracy. Our breakthrough starts with an observation about how this model actually thinks. If you ask a model about a specific detailed document, it doesn't actually attend to every single word with equal weight. Attention is sparse, usually less than 5% of these tokens in the history are actually relevant to the next word. If we can identify those important tokens and keep only them in the fast memory, we could theoretically run massive context on a tiny GPU. So why not just put the rest on the SSD? Because of the high latency gap. Accessing VRAM takes nanoseconds, while accessing a SSD takes hundreds of microseconds. When the GPU is waiting for a token from the SSD, it's doing zero work. If we use a NIP on-demand loading strategy, the user ends up waiting seconds for every single word. And as we all know, SSD achieve optimal performance only with sequential and coarse-grained operations. So the tiny and random reads caused by attention sparsity cannot fully utilize the SSD bandwidth potential. Existing research like Zheng tries to fix this by hiding the SSD latency behind other works, but they rely on high concurrency, processing 30 or 60 users at the same time. But on a personal PC, you are the only user. With a batch size of 1, there isn't enough computation workloads to hide the I/O latency, right? So to solve this problem, so attention's core philosophy is co-design. We don't treat the sparse attention algorithm and the storage management as separate layers. We align the data structure of the cache cache with the physical page side of the SSD. We transform those random tiny reads into coarse-grained sequential transfers. And we also pre-select and prefetch the cache blocks in advance to leave sufficient time for I/O computation overlap. But there is several challenges. The first is the accuracy efficiency trade-off. This is a fundamental conflict between model precision and hardware support. To maximize the SSD performance, data must be transferred in large, sequential blocks. However, sparse attention requires selecting specific important tokens. If we compress multiple tokens into one block, it means we might lose critical outlier tokens, causing accuracy to plummet. And the second challenge is the prefetching indeterminacy. Because attention is reactive, the model cannot identify which KV blocks it needs for a specific layer until the previous layer's calculations are finished. This means the GPU remains idle while waiting for the SSD to transfer data. In low batch environment, this lack of foresight prevent prefetching and break the I/O computation overlap. And the final strategy is the data inconsistency risk. Running I/O and computation in parallel with highly constrained memory creates a safety risk. Since the RAM is limited, we cannot afford massive buffers. This creates a race condition that the SSD controller might override a buffer with pre-fetched data for the next year before the GPU has finished reading the current data. Without a sophisticated synchronization, the system faces a choice between losing performance to locks or risking inconsistency. And the final challenge is running I/O and computation in parallel will introduce the data inconsistency risk. When I/O and computation are running in parallel with highly constrained memory, it creates a safety risk. Since the RAM is limited, we cannot afford massive buffers, right? This creates a race condition. The SD controller might override a buffer with prefetched data before the GPU has finished reading the current data. Without sophisticated synchronization, the system faces a choice between losing performance to logs or risking inconsistency. So we to deal with this challenge, we need to answer three questions. How to fully utilize the SD bandwidth, how to reduce the cache loading latency, and how to efficiently overlap I/O and computation. Here is our layered architecture. We remain the full cache on the SSD, a waiting room in the DRAM, and a tiny active set in the VRAM. We propose three components to answer this question, like the KV consolidator consolidates multiple KV cache entries to enlarge the SSD transfer unit to fully utilize the SSD bandwidth. And the system also uses the speculative prefetcher to predict and prefetch the KV cache, while SSD-aware scheduler to orchestrating the fine-grained computation I/O overlap according to their data dependencies. So let's look at how these components actually work. First, we adjust the I/O efficiency through KV interleaving. Traditionally, keys and values are stored in separate memory regions. This requires two separate SSD reads. We've redesigned the layout to interleave them, and the keys and values are loaded and stored as an integration. Also, to avoid the runtime overhead of reordering, we actually fuse the weight matrix offline. This means when the GPU generates the next token, it's spawned in an interleaved format. We then read it back using threaded access, which allows us to compute the tension without ever needing to physically reorder the data in the memory. Next, how do we prefetch the KV cache? We discovered that the token selection has temporal locality. If a token was important in step 1, there is an 81% chance it is still important in step 2. We explore this by speculative loading the top K blocks from the previous steps, like the init block and local block. They are determined to involve in the attention computation. We prefetch it directly. But for the selected blocks, we cannot determine which to load, so we prefetch them according to the selection history. But there is another question. The selected block may change during the inference, right? So to keep the accuracy of inference, we reload it according to the selection result, and directly override rows fetched by mistake. Because out of order KV cache doesn't impact attention computation. We even no need to reorder it constantly. Finally, we have the scheduler to mitigate the synchronization issues. That the introduction of dynamic attention sparsity that cause frequent low latency SSD accesses and massive synchronization points. We don't treat attention as one big task. On the other hand, we break it into micro tasks: projection, selection, loading, and computation. This allows us to start loading the next layer's KV pairs, while the current layer is still doing its calculation. Also, to reduce the GPU synchronization overheads, we also group the operations not in the critical paths with those critical tasks, so that they can share the same synchronization points and reduce the synchronization overheads. Finally, we test SolidAttention on the hardware most people probably owns, an RTX 4070 laptop GPU and an Intel integrated GPU. We pushed this system to a 128K contacts, which is a limitation of most existing open source models. For the end-to-end performance, SolidAttention achieved up to 3 times higher throughput than other baselines, not only on the discrete GPU, and also the integrated GPU. As for the memory occupation, we reduced the KVCAche footprint by about 98%. It means that we kept an 16 GB contacts running in just about 200 MB of active VRAM. To further evaluate the overheads introduced by SSD offloading under the effect of SSD aware scheduler, we also compare the performance of SolidAttention and its in-memory counterparts. These counterparts place the whole cache in the memories so that it do not need to afford the latency of SSD accesses. The evaluation results show that SolidAttention experienced less than 11% throughput degradation despite SSD overloading. Under the introduction of attention sparsity, successfully reduced the computation workloads so that SolidAttention's performance remains stable even with the context length increase. We also evaluate the inference accuracy of SolidAttention and other inference frameworks. We use the benchmark like MLU, GSM-8K, such common benchmarks, and the long context benchmarks like long bench. This can test the model accuracy with 60K context length. And the evaluation results show that SolidAttention kept model accuracy even with long context length compared to the inference without the attention sparsity. Yeah. However, the consolidation method fails in most of benchmarks, especially with long context inference. In summary, SolidAttention proved that the memory war isn't just about how much RAM you can buy. It's about how smart you are with the storage you already have. By co-designing sparsity and I/O, we bring the 128K context model to the 60 GB laptops of the world. As local AI becomes the norm, this technique will be the foundation for truly private existence. Thanks for your listening. If you have any question about our project, feel free to contact us using email. Thank you.